Hello and welcome to the third part of Lesson 4 in Unit 6, Solving Problems with Quadratics in our Grade 10 Academic Math class. So in this particular lesson we've gone over solving problems using factoring or quadratic formula. The lessons before this we talked about solving optimization problems. Optimization problems, we're talking about finding max and min, which is like code for vertex, which means we need to go from standard form to vertex form by completing the square. Solving is a different beast. Solving means finding the values that make the left side of the equation equal to the right side. We solve our quadratics by factoring or using the quadratic formula. So we've been lucky so far. The first two examples we did here, we were able to factor our solutions, or factor to get our solutions. And now we're going to head on to the lidless box, and I have a feeling that this one's going to be a quadratic formula. Okay, so I do want to start by saying this is everybody's least favorite type of quadratic word problem, in my experience. It's because I think it's a little bit difficult to wrap your head around what's happening. So I've done a little bit of pre-drawing here. The question itself isn't as important necessarily as understanding what this drawing represents. So take a sec, hit pause, copy this thing down as far as I've got it so far, and then we'll talk a little bit about how to set this up and then how to solve it. So go do that now. Okay, you're back. So the first thing I want you to understand is that lidless box questions, you need to consider that we're making a three-dimensional shape, which is hard to sort of visualize in our heads sometimes. So what I've done here is I've drawn it in two ways. I've drawn it, well, let's read the question first. A lidless box is to be constructed from a square piece of tin by cutting a 10 centimeter square from each corner and bending up the sides for the box. If the volume of the box is 1200 centimeters cubed, find the dimensions of the original sheet of tin to the nearest centimeter. So what I'd like you to imagine is that this is that original square of tin. Now we don't actually know how wide it is, but we do know that 10 centimeters were taken off of each side. So 10 centimeters were taken off of each of those sides, and 10 centimeters were taken off of each of those sides as well. And it results in this sort of interior square. Because remember, these parts that I've shaded in, they're gone, right? They're not there. So you've got this thing that kind of just has these flaps. Now each of these flaps is then, so I'll try to see if I can erase this. I don't remember how I drew it. Nope, I didn't do a very good job of drawing it. So let's just jump over to the other piece. So imagine that this part down here, this was that original bottom of the box here. And I've folded this side up to make this side, and I folded this side over here up to make this side, and I folded this side over here up to make this side, and I guess we'll do the fourth one too. I folded this side over here up to make this side. So I've created a box, but it doesn't have a lid. So the piece of information that we've been given outside the fact that this is made from a square piece of tin is the volume of this box is 1200 centimeters cubed. So I've taken the, I've pre-written in our volume formula for a rectangular prism, which is length times width times height. And we know that our volume is going to be 1200. So I've already sort of popped that in there for us. And then we have these x minus 20, and 10. So I want to talk about those dimensions first. Oh, I guess also our let statement is let x represent the original side lengths of the tin square. I've sort of drawn that in here. So again, how would we determine this dimension? So again, we're dealing with a volume, right? We want to know what this length is. I'm going to change up my colors here. It's getting too green in this party here. So I want to know how long is this here. That corresponds to this piece right here. So that is an original x, and we took away 10, that's this little piece over here, and then we took away another 10, and that's a little piece here. So that's going to equal x minus 20. That's where this guy here came from, length times width, or sorry, the length rather. And then we're going to do the same thing on the other side. What is the dimension over here? Well, again, I know that we started with an x, and then we took 10 off down here, and we took 10 off up here, so this will also equal x minus 20. That's where the thinking comes from. And again, not dissimilar from this question up here, where we're talking about generating some side lengths, our side and our length and our width rather, considering these uniform pieces that are being added to it. This one, it just so happens that the interior happens to be the variable that we're after, and we're taking off a known amount on the sides, but it's the same idea. And so that width then becomes over here, x minus 20, and as we know, when we fold these things up, so remember, if we're folding this side here up, that's going to have a height of 10, and that's where this 10 here comes from. It's the height of the box, which again is sort of one of those two sides that were cut out of the corners. I totally understand that this is a confusing setup, but now that we've got it set up, we're in a great place to kind of expand this thing out and go for a solve here. So we have 1200, I'm just going to do a rewrite over here. We have our 1200 equals x minus 20, and then 10 times 10. So we are going to expand this thing out, and we're going to gather together our like terms. So let's get our 1200, and we are going to have x squared minus 20x minus another 20x plus 400, and this whole thing is going to be multiplied by 10. So let's keep rocking on that. Now, people always ask us, is it okay to divide both sides by 10 at this point? It absolutely is. It's an equation, so it does follow the rules of equations. So would it be a little bit easier to maybe divide by 10 rather than factoring it out later? Yep, probably, but we're going to do it the other way. We're going to just sort of expand the whole thing out just to sort of see that it works. So here we have our 1200. Here we have our x squared minus 40x plus 400 times 10. So now we're going to distribute that 10 through, and at the same time I'm going to do a bit of a cheater step here. I'm going to bring the 1200 over to the other side by subtracting 1200. So we're going to have 0 equal to 10x squared minus 400x plus 4000 minus 1200. That's the 1200 from the other side. So let's gather together, or I guess just simplify that little bit at the end there, and that's going to give us 2800. Okay, so now we're in a position where we have ourselves a pretty good looking quadratic here. We're definitely going to factor it out. So again, I just wanted to reiterate, it's not absolutely crucial to divide out by 10, but you can if you'd like. So here we're going to factor out 10. There's 10. We're left with x squared minus 40x plus 280. And now we're being asked to solve. So let's go after our discriminant again. I think we actually have space this time. Man, do we have a lot of space. Okay, let's go do the discriminant. So the discriminant is equal to our b value squared minus 4 times a times c. And let's see if this comes out to a perfect square. So again, I'm just going to type this whole mess into my calculator. That's going to be negative 40 squared minus 4 times 1 times 280, and that's going to equal 480. And I'm going to square root that. I'm going to see if it's a perfect square. I don't think that it is. And it is not. So we are going to say, since d is not equal to a perfect square, therefore solve using quadratic formula. All about the short forms. Okay, so now we're going to use the quadratic formula. I'm going to go horizontally here, I think, just to get her in there. So we have our, yeah, there's enough space, I think. So we are going to do x equals negative b. So there is our b value is negative 40, so minus 40, plus or minus the square root of minus 40 squared, minus 4 times a times 280. Now what's nice is since we've already found the discriminant, we know what it's equal to, so we don't actually have to do that calculation a second time. Just checking to make sure I did my substitution right. Okay, that looks decent. So we are going to get 40 plus the square root of 480 all over 2. And again, the reason I knew that it was going to be 480 was because I actually calculated the discriminant over here, and that's all the same stuff that's under the radical sign. So let's go about solving here. We have a first scenario where x will be equal to 40 oh sorry, I forgot my minus up there, 40 plus root 480 all over 2, and scenario 2 where you've got x equals 40 minus root 480 all over 2. Let's work these through in the calculator. Again, I'm going to do it all in one step. I'm going to hit a hard return after my numerator just to make sure my calculation is correct. So we have 40 plus the square root of 480. That's going to equal 61.9, etc. And then we divide by 2. And that's going to give us, I'm going to round to one decimal place here. So that's going to be, oh, that should be 31. So 31.0 approximately. And let's do the same thing on the other side here. So we have 40 minus the square root of 480 is equal to 18.09, and I divide that by 2, and I get 9.0 approximately. So x equals approximately 9.0. Okay, now on the surface, both of these solutions look just fine. But here's what I'd like you to consider, is that the x value that we're trying to find here represents the whole original side of the tin square. And we took 10 centimeters of tin off of each side. So if our original value for the side length was 31, whoops, that should be a highlighter. If it was 31, we can take 10 away twice. That's no problem. But if we have 9, we can't actually take 10 away twice, which makes this particular solution inadmissible. Inadmissible. And I'm just going to write a little note on it, so I would like you to write it in there as well. You can't subtract 20 from 9. I can't subtract 20 from 9. So that particular value is inadmissible. It means that our original dimensions, therefore the original tin square was 31 centimeters by 31 centimeters. All right, and there is our therefore statement that finishes up a challenging problem, I think, from this unit. As I said, I think it's people's least favorite. It's hard to set up, but the math itself is pretty straightforward once you get into it. So by all means, rewatch portions of the video. Email me if you have any questions. Otherwise, good luck with the homework, and we'll see you in lesson number 5.